Okay, let's start then. Yeah, hello everybody again. Welcome to the fourth installment of the HBP Tea Slides. My name is Alper Jenole and I'm the chair of this session. So as usual, before we start with our two talks, I would like to shortly introduce the session format. So we will hear two talks of 10 minutes. After each of these talks, there will be short time, roughly 5 minutes, to ask the speakers for questions, and then we will switch to the next talk. But in the end, there is still time that you can ask your questions because the speakers are still available, and you can also discuss there. So if you have a question, you can click on the question and answer and type in your question there. And then I will pass that to the speaker. But also feel encouraged to raise your hand. So you can also do that in the question and answer. And then directly with your microphone, you can ask the presenter your question. So this session will also be recorded and later available at the e-library of the education webpage and also on YouTube. So also be sure to subscribe there. If there are any technical problems or if you think you have good ideas to improve this session, you can also write directly to the education team in an email. So please write to education@humanbrainproject.eu. All right, so let's start with the first talk by Petruț Bogdan. Peter is a PhD student at the University of Manchester in the Computer Science department, and he will present SpiNNaker, a spiking neural network. Please.
Thank you, Alper, but I am now a postdoc.
Sorry about that. Peter is a postdoc now. Good.
Don't worry about it.
Congratulations.
Thank you. Can you see this?
Yes.
Okay. So, hello, everyone. My name is Petruț, or Peter, whichever is easiest for you. Thank you for coming to today's HBP Tea Slide session. For this presentation, I brought a nice silver needle tea to stay on brand with the event. I hope you have something warm with you as well. This talk will be a very quick overview of the SpiNNaker neuromorphic computing platform with an equally fast presentation of a fun result from my PhD at the end. The narrative thread of this presentation generally follows the chapter organization of the open access book with the same name as the presentation, of which I'm very proud of, and thus raising its visibility here. The QR code in the corner takes you to the publisher's website if you'd like to read more about it. Geomorphic systems generally can be understood as being brain-inspired, with two overarching questions driving the research in this space, at least for us. So can massively parallel computing resources accelerate our understanding of brain function? This is done through advances in theoretical neuroscience, for example, by hypothesizing about principles of execution of particular brain functions or circuits, testing the prediction in simulation, followed by validating or invalidating against experimental evidence. And the other question is, can our growing understanding of brain function point the way to more efficient, parallel, fault-tolerant computation? Of course, we want our computers to use less energy per task, be fault-tolerant in the sense that if something breaks, there is sort of graceful degradation, and be able to do a large number of things in parallel. The SpiNNaker project was born of these pursuits. To begin with, a chip was designed that would use 18 ARM processing cores to efficiently simulate spiking neural networks. While the platform is digital to allow maximal flexibility of the neural applications run on it, some architectural features are bio-inspired, such as the fact that data is co-located with the processor, so data doesn't move very far to be processed. The chip is composed of relatively low power and cheap processing units, sort of analogs of neurons, although they routinely simulate approximately 100 neurons each. The system is fault tolerant in that it can still function, although chips routinely have a core missing. So it's broken from when it was created. And finally, spike transfer between neurons on different chips and cores is optimized for the task at hand. The routing system designed for SpiNNaker can be considered its special sauce, if you'd like. The key technique used in the router is a ternary content addressable memory, a TCAM, which looks at information contained in the spike packet and determines where it should go. Each core has one of these routers, and that's how spikes can hop from chip to chip to reach their generally numerous destinations. A biological equivalent of this subunit could be seen as an associative memory. In this case, the router associates an incoming packet with one or multiple destinations. Single chips, however, are not particularly interesting. Thus, bigger machines were constructed to allow large-scale spiking neural network applications, starting from individual chips, then to boards incorporating 48 of these chips to create a scalable compute unit, which are then wired together to form the originally promised 1 million Armcore machine. This machine is hosted at the University of Manchester, but it's accessible by anyone from anywhere in the world via the Human Brain Project Laboratory. We also have instructions on how to do this on our website. The QR code in the corner links to a video that we released to celebrate its completion. And there you can see a time lapse of us wiring up this beast. It took the better part of a week, although we didn't work full time because we were still PhD students and had other work to do. The scale of the system, as well as its digital nature, allow for a varied and wide range of applications. I actually don't have enough space on this slide to include all the different neurobotics, computational and theoretical neuroscience applications and experiments that have been run on the machine. Instead, I would like to focus on a possible and, in my opinion, very interesting solution to the problem of apparent motion detection and resolving the direction of that motion. I propose, and I only have time to convince you through intuition, of the fact that you can achieve this in an unsupervised fashion by creating synapses through structural plasticity that draw from a distribution of synaptic delays. So you can have individual neurons be tuned to respond to particular movement directions by growing synapses continuously over time and pruning away those synapses which are not useful, as decided by STDP. So let's develop that intuition. This is the task, but even more simplified than what I showed in the previous slide. A single neuron needs to detect the moving stimulus using its limited receptive field. For this, it needs some synapses. So let's add some synapses. Oh, yeah. Let's see how the motion can be encoded. So each of those input neurons spike. And now we add some synapses. If all the synapses take the same amount of time to transmit the spike information to the neuron, but the input is sparse and moving, so the input comes from different neurons over time, then the spikes will arrive at the neuron desynchronized. And the neuron won't fire, and thus no detection of movement has been achieved. If, however, you simply we can engineer this. If you arrange the spikes so that they take a different and appropriate amount of time to carry the spike signal to the neuron, then the spikes can arrive in a synchronous fashion at the cell, allowing for detection. Placing many of these neurons that continuously rewire their connectivity to select for the appropriate sets of delays for the stimulus they receive allows them to self-organize and become tuned to the statistics of the input. I've tested this behavior with different directions, with varied levels of noise and jitter on the input, but I'm confident this approach is adaptable for different input shapes and speeds, for example, as well. And I don't have time to show you all of the analysis or any of the analysis for these experiments. They're available elsewhere. I also want to give a shout out to a recent paper that covers several different approaches for tackling spatiotemporal pattern classification with spiking neural networks. This is generally a problem in this field that a lot of people use sort of rate-coded neurons, which not the best for transmitting information or for the efficiency of the hardware. But this paper proposes several techniques to deal with this kind of data that is precise spike time based. Two of the techniques used in this paper were synaptic delay plasticity, so a scenario in which delays are plastic but connectivity is static, and structural plasticity, where delays are static but connectivity is plastic. So the approach I showed the slide earlier combines these two worlds, sort of. The task that they use in touch localization, the task that they use in the paper is touch localization for a model of a sand scorpion. However, they should be more widely applicable for precise spike timing applications in general. Summarize, we built neuromorphic hardware to make computation more efficient and to advance our understanding of the brain. SpiNNaker is a 1 million Armcore digital neuromorphic machine currently in use to explore theoretical and computational neuroscience simulations and neurorobotics applications. Various models of synaptic and structural plasticity are and can be implemented on this platform, again, because of the digital substrate, which offers flexibility in exchange for some power efficiency. And structural plasticity is a cool learning mechanism that can be used to grow synapses with different synaptic delays to optimize neuron responses to spatiotemporal patterns in general and movement in particular. Thank you.
All right, thank you for your talk. So I would take questions. Are there any questions so far? I don't see them yet. Maybe I can ask a general question. Peter, do you see any synergies also regarding high-performance computers? So are there any collaborations between SpiNNaker and high-performance computing?
Could you please repeat the first part of the question? I couldn't hear a couple of words.
I just asked if there is any collaboration between HPC and SpiNNaker, if there are any synergies between those, and if so, how can you utilize those?
So collaborations and synergies, we've had collaborations in the past, and I believe there are going to be more in the future, where we've compared simulators such as NEST against SpiNNaker and how that works, and what the results are for that, and also discussions on how to do code generation for different simulation platforms, and that would allow for quicker implementation of models and all of that. In terms of how you could use both of them, there are ongoing efforts to use neuromorphic platforms as accelerators for spiking neural networks, while the high-performance computers do something that they're arguably better at, raw number crunching at large scale. So they could do something like learning to learn. So there would be an evolutionary algorithm on HPC and spiking networks on neuromorphic. But SpiNNaker is not directly involved in that particular pursuit at the moment. Other HPC and SpiNNaker collaborations, I cannot think of right now, except generally validation between the two platforms to see that neuromorphic computing can give similar or the same, and in any case, comparable results to what an HPC system would give.
Okay, thank you. We have a question from Trang Ang Ningheim. He asks, nice talk. Do you think that spiking architectures are particularly appropriate to encode motion perception compared to conventional architectures of today's computers?
So the reason why, yes, so in short, yes, I believe spiking networks should be able, this is one of the areas in which they should be better suited than conventional techniques like deep neural networks, maybe recurrent neural networks, because they have this inherent time component inside of the neurons and the synapses and the system. Time models itself in our networks. So for precise spike timing applications or applications such as this, where the input is encoded appropriately with fewer spikes, something like a event-based camera, for appropriate inputs, spiking neural networks should be very good at this. For frame-based vision, the conversion to a format that spiking neural networks prefer to operate with, or want to operate with, can be cumbersome and lose some of the detail that an event-based sensor would gain. So yes and no. I guess that's the answer. Yes, if your input is correct. No, if you're doing something weird.
Okay, thank you. Yeah, if there are other questions, we can ask them later on. There was a question to Peter by Karim Kuban, and he was asking: are the live neurons that you're are these live neuron LIF neurons that you are simulating? What about dendritic computing and more detailed neural models? Is SpiNNaker scalable to these as well? And have you ever tried to simulate them? For me, backpropagating action potentials and dendritic computing is a crucial part of brain simulations where spiking neural networks cannot account for.
So yes, these are leaky integrate and fire neurons that we normally use on SpiNNaker. What about dendritic computing? So we have a lot of interest in our group in dendritic computation and how multi-compartment models can be simulated and how they process information. And I think we have someone, a PhD student in the lab, working on a 2-compartment neuron model right now, and someone else exploring multi-compartment models. A lot of the driving force for the models that we implement, I believe there's a shift in our group, at least, that we would like more input from the community. It's very easy for a group like any group, really, to build its own echo chamber, and bouncing ideas off of each other is not the most productive thing. So we are very interested in dendritic computation, and we await the models and experiments that you would like to implement. Get in touch and maybe we can do something. There is no reason why multi-compartment models cannot be implemented on SpiNNaker, except if the computation performed by individual parts is maybe too complex, that maybe it can't fit in the instruction memory or the time requirements of the simulation. But otherwise, we have a generic computer that just happens to have 1 million cores. Everything that is computable and can fit on it should run. We have partnerships or at least discussions with Panayota Poeratsi in, I think, Crete, with someone in our group visiting and discussing dendritic computation. And I'd certainly be very interested to see something like this. We can't just do it. We need your input.
Okay. And I have a question also for you, Peter. So let's say I have a model and I would like to run this on SpiNNaker. What do I have to do? I mean, I can contact you, yes, but what steps are needed otherwise?
So we've tried, with the help of the HBP, to make it as easy as possible to do all of this. The current requirements are you need an HBP collaboratory account and a browser. There might be the extra complicating technicality that you might have to submit a photo of your passport to some internal thing to validate that you're not using it for nefarious reasons, but we don't actually enforce that. So we have 2 different systems where you can use SpiNNaker. We have a Jupyter notebook that runs on a server here in Manchester that doesn't require you to submit a passport. And the HBP collaboratory that the generic way of accessing through the HBP. And then this remote access allows you to use software. No, actually, I think you can do most everything that you could do locally with that kind of system. So you can implement your own neuron models and learning rules, or you can build networks out of the components, the neurons and the synapse types that we already have available, and build the systems that you want. Further, we have a neurorobotics environment attached, so tightly coupled with the Jupyter environment, so you can run experiments with virtual pushbots or Husky robots or whatever you'd like, with event-based cameras or not, or and everything would be very close. So the response time of the robots or of the SpiNNaker should be good enough, because they're in the same room. So really, there's websites, there's tools, and there's a really low barrier of entry, I believe.
Thank you, Peter. I'm already looking at the time, and it's quite late already. So I think we can slowly finish then our session. I would then again thank our presenters and speakers. For everybody else, if you have other questions, you can reach, of course, the speakers via email, or you can also just write the education team. Yeah, as I said in the beginning, if there is any wishes to improve the format of this session, also write an email to the education team. Or you can also join our Slack channel, and then you can also connect, of course, to other students and other researchers. If you want to present your own work, also feel free to send the education team an email, and then we will come back to you. In the end, when you close basically the session or log out the sessions, then there will be a survey. Please fill that out, because this is valuable information for us. Yeah, and thank you for listening, and hope to see you again next time. Thank you, everybody. Bye.
Bye.
Thank you. Bye.